In our final example here, we are going to take a look at a 3 by 3, and the process is very similar. The eigenequation does not force us to be restricted to 2 by 2s. In fact, it doesn't have any information about dimensions other than a has to be square. So once again, we want the determinant of a minus lambda I to equal 0. So a minus lambda I, and I'm going to go ahead and write this out, lambda I will be lambda I will equal the, well, let me write this out, 2, 0, 0, 0, 4, 5, 0, 4, 3, minus lambda times I, so that the three-dimensional identity matrix will be 1 along the diagonal, 0 everywhere else. So here I'll have lambda, 0, 0, 0, lambda, 0, and 0, 0, lambda. And that's going to be my a minus lambda I, and once again I want the determinant of that quantity to be equal to 0. So the determinant, the matrix that I want the determinant of is 2 minus lambda, 0, 0, so 0 minus 0, 0 minus 0, and then again 0, 4 minus lambda, 5 minus 0, 0 minus 0, 4 minus 0, and 3 minus lambda. And I want the determinant of that to equal 0. Now to find the determinant of a 3 by 3, we first of all alternate signs between terms, and the first component that we grab, recall, is we take the 2 minus lambda and we multiply it by the determinant of what's left after you cross out that row and that column. So this will end up being 2 minus lambda times the determinant of what's in the rectangle here, which is 4 minus lambda times 3 minus lambda minus 4 times 5. And that is the first step. The next step is then to, so this is going to have a plus in front of it, so that's for the first column, we just alternate signs. Now we're going to go minus, that's the second term, and to do the second term we have to look at the next column. Let's get rid of some of these little guys here. Let's see if I can do this. Now we're going to use the 0 as our pivot, cross out that column, cross out this row, and then find the determinant of what we have between 0, 0, 5, 3 minus lambda. So this is going to be 0 times bracket 0 times 3 minus lambda. You can see where this is going. This is going to 0 out, but we're still doing it. Minus 0 times 5. And the next thing that we have to do is when we close that bracket is now we have to add the coefficient of the third column. So we're going to do plus, and I'm going to come in here and again delete some of these things so that we have a fresh start. So delete that, take care of these guys here, and now we are going to again be dealing with a 0. So to find the determinant of that, here I'm going to have 0, cross out that row, cross out that column, so plus is the sign, 0 times bracket the determinant of what's inside of here, which will be 0 times 4 minus 0 times 4 minus lambda, and you can see that that's also going to be 0. Now that's the determinant of this whole matrix right here, and I want to set that equal to 0 and solve. So this term here is going to be 0, because that whole thing is being scaled by 0. This whole term is going to be 0. You can imagine how messy this would get if we didn't have that. And then all I want to solve is 2 minus lambda times bracket 4 minus lambda, 3 minus lambda, minus 20. I want that equal to 0, and I want to solve for lambda. Now this is going to be you can see you're going to have a lambda cubed in here, and a cubic polynomial will have 3 roots. Again, some of those could be complex in general, some of those could be repeated, but now we're going to go ahead and solve this, and unfortunately doing this by hand is going to become kind of difficult solving cubic polynomials, so I've just input this into Wolfram Alpha, and I get 3 lambda values. Lambda 1 equals -1, lambda 2 equals 2 and lambda 3 equals 8. So now I'm going to calculate v1 for lambda 1 equals negative 1. And this is going to be the identical process, and I'll have to do it for v2 for lambda 2 equals 2, and v3 for lambda 3 equals 8. So that means that if I plug in into my A minus lambda I matrix, I plug in negative 1. So there's my A minus lambda I matrix. That's this guy here. So I'm going to do 2 minus lambda, 2 minus my lambda, 0, 0 across the top, 0, 4 minus lambda, and 5, and finally the last row, 0, 4, 3 minus my lambda, which again is negative 1. And remember, the polynomial that we're trying to solve is x, y, z, or this is our v1 in this case, is equal to the 0 vector. So this matrix is going to give me, if I start to reduce this and set it up as a Gaussian elimination problem, I'll have 3, 0, 0, 0, 5, 5, 0, 4, 3 minus negative 1 is 4. And so if we perform, oh, and then I want to augment this by the 0 vector because I'm trying to find the coefficients of x, y, z. So I'll have the 0 vector here, and that in reduced form will produce us with, and so here's the matrix that we get. We can again see that it has infinitely many solutions because the second equation, the first one says x has to equal 0. The second equation says y plus z has to equal 0. And the third one says 0 equals 0. So that means x has to be 0. That's already given. But there's no constraint on what z has to be. So we just need to make sure that y plus z adds up to 0. So z is a free variable. And we'll say let z equal c. So what that will give us is we'll have our v1 vector, which is equal to x, y, z. So x has to be 0. Now, y plus z has to equal 0, so that means we assigned z to be a free value. So y has to equal the negative of z, so it has to equal the negative of that value. And so any vector of this form will work. So again, I'm just going to choose, I think negative 1 will, or sorry, c equals 1 will work great here. And so we'll get v1 equals 0, negative 1, 1. Now we won't repeat this here for the remaining two eigenvalues. You can see the process is identical, and we would just get 2 more eigenvectors from these two guys. But I wanted to demonstrate that you end up seeing the same kind of process emerge, just obviously it gets a little bit more chaotic. Now just to verify as a check that this is in fact an eigenvector that we found, if I look at the original matrix, which was 2, 0, 0, 0, 4, 5, 0, 4, 3, and I multiply it by what I'm claiming to be an eigenvector, 0, negative 1, 1, and if I do that, I am going to get, let's see, this will be negative 4 plus 5. This one will be 0. Negative 4 plus 5 is 1. Negative 4 plus 3 is negative 1. And you can see that what's come out is negative 1 times our 0, negative 1, 1 vector. And since the input and the output are just scaled factors of one another, we have been able to confirm that this in fact is an eigenvalue eigenvector pair where my lambda, as we can see, is equal to negative 1. Now the last thing I want to make us aware of is that oftentimes rounding eigenvalues is pretty dangerous. And this is kind of one of the common issues in linear algebra, is that if you look at, for example, the matrix 1, 2, 3, 4, and I'm going to skip a couple steps here, but if I do the determinant of A minus lambda I, which maybe you're even noticing by now will just be 1 minus lambda, 2, 3, and 4 minus lambda, and I set this equal to 0, I will get lambda 1 is equal to 5 halves minus the square root of 33 over 2. And lambda 2 is the same thing, 5 halves, but plus square root of 33 over 2. Now, these are exact values. Square root of 33 is irrational, but if I were to approximate these and said, well, I don't want to work with these ugly values, I'm going to make this about negative 0.37, and this is about 5.4 if we round. And if I were now to go and find the eigenvectors, so v1 for lambda 1 equals negative 0.37, here's what would happen. I would get 1 minus lambda, which is 1 plus 0.37, or 1.37, 2, 3, and then 4 minus negative 0.37 would be 4.37. And here's my eigenvector, xy, the components I'm trying to solve for, equals 0, 0. And when I go about reducing this, I am going to get, let's see, 1.37 to 3, 4.37, augmented by 0, 0, perform Gaussian elimination, and you actually end up with 1, 0, 0, 0, 1, 0. Now that does not tell me there are infinitely many solutions. In fact, if you even look at the relationship between these two, they're not perfect scale factors. They're not linearly dependent. So that means we're going to only get one solution if it's a linearly independent matrix right here. And you can compute the determinant and see they don't quite cancel out. So this says x equals 0, y equals 0. And so we get the trivial solution only. So what's the key here? Don't round. If you do, you are going to end up with this problem.